Hey everyone, and welcome. Today, we're going on a kind of expedition into the heart of mathematics. We're going to learn the language that science literally uses to describe our universe. So, you ready? Let's dive in.
Just think about it for a second. Everything is always in motion, right? A planet zipping around the sun, a cup of coffee cooling on your desk, even the stock market. It's all constantly changing. So how on earth do you capture that kind of dynamic, moving reality with something as static as an equation?
Well, it turns out math has this incredibly powerful dialect that's built just for this. It's the language of derivatives. And derivative is just a kind of fancy word for a rate of change at a single instant. These are called differential equations, and trust me, they're less like scary formulas and more like stories. Stories about how things change from one moment to the very next.
And you know what the best part is? You absolutely do not need to be a math whiz to get the hang of this. This is your field guide. In the next few minutes, I'm going to show you how to spot these things in the wild and actually understand what they're telling us. So, let's get going.
Okay, so first stop on our expedition, basic identification. Before we can figure out what these equations do, we've got to know what they are. What does one look like? What are its tells?
So here it is, the textbook definition. Sounds a little dense, I know, but let's break it down. Imagine a car driving down the road. The distance it's traveled, that's the dependent variable, because it depends on how much time has passed, right? So time is the independent variable. A differential equation, then, is what connects those things using a derivative, a term that tells you the car's exact speed at any given moment. It's also really important to learn how to spot imposters. So on the left, we've got a genuine differential equation. See how it sets up a specific relationship between the rate of change of y and the variable x? But the thing on the right, well, that's an identity. If you actually do the math on the left side, you'll find it's always the same as the right side. It's just a mathematical fact, not a dynamic puzzle we need to solve.
Okay, great. Now that we know how to spot a real differential equation, let's talk about its two main families. You can think of it like classifying animals. Does it have fur or feathers? Here we ask, is it ordinary or is it partial? An ordinary differential equation, or ODE for short, is the simpler one. It describes something that depends on only one independent variable. So think of it like tracking a single baseball's flight through the air over time. A partial differential equation, or PDE, is a bit more complex. It's for when you have two or more independent variables. This is more like a weather map, where the temperature depends on both your latitude and your longitude.
And the notation itself kind of gives you a big clue. In that OD, see the plain straight D? That's your signal that we're talking about a derivative with respect to just one variable, x. But in the PDE, you see that curly del symbol? That's a partial derivative, and it's telling you that our variable v is changing based on multiple other variables, in this case, both x and y.
All right, so once we've figured out the family, ODE or PDE, we can zoom in a little closer and check its vital stats. For our field guide, the two most important stats are going to be its order and its degree. The order is super easy, seriously. You just scan the whole equation and find the highest derivative there is. In this example, you can see a third derivative, that d cubed y over dx cubed term, and you see a second derivative. Well, 3 is higher than 2, so the order is 3. That's it.
Next up is the degree. The process is pretty simple. First, you find that highest order derivative again, the same one we just found. For us, that's the third derivative. Then you just look at what power it's being raised to, and right there, you can see it's being squared. So the degree is 2. The key is to only look at the power of the highest order derivative. Ignore everything else.
But there is one little trap you gotta watch out for. You can only figure out the degree after the equation is free from any radicals. Like square roots or cube roots that might be messing with your derivatives. So if a derivative is stuck inside a square root, you have to get rid of that first, like by squaring both sides of the equation, before you can correctly say what the degree is.
We have just one last classification for our field guide. This one tells us about the equation's times behavior. Is it predictable and, well, kind of straight-laced? We call that linear. Or is it more complex, maybe even chaotic? That's what we call nonlinear. And this difference is a huge deal, because nonlinear systems are where things get really wild, describing everything from turbulent water to weather patterns.
So, an equation is linear if it plays by two simple rules. Rule number 1, the dependent variable, usually y, and all of its derivatives can only show up to the first power. No y squared, no y cubed. Rule number 2, you can't have y and its derivatives multiplied together. If an equation breaks even just one of those rules, boom, it's nonlinear.
This table makes it pretty darn clear. The top equation, totally linear. The y and its derivative are both just to the first power. Simple. But now look at the bottom one. If you were to multiply out that x plus y squared part, you'd end up with a term that has y squared in it, which is then multiplied by dy dx. That breaks both our rules, so this equation is definitely nonlinear.
So, we've learned how to spot them, classify them, and categorize them. But why? What's the point of this whole hunt? Well, the ultimate goal, the whole reason we do this, is to find a solution. But what does that even mean in this context?
Okay, this right here is probably the most important idea to get. If I give you an algebra problem like x plus 2 equals 5, the solution is a number, right? X equals 3. But the solution to a differential equation is not a number. It's an entire function. It's the whole story the equation was trying to tell you, the complete description of a behavior over time or space.
Let's actually put this to the test. Our equation, dy over dx equals y, is famous. It describes things that grow exponentially. Now, let's say someone proposes a solution, the function y equals cex. To check it, we just follow the steps. First, let's take the derivative of our proposed solution. Well, the derivative of cex is just cex. Easy enough. Now, we plug that and the original function back into our equation, and we get cex equals cex. The left side equals the right side. It's a perfect match. That means our function is a totally valid solution.
But one final heads up for your expedition. Not every equation actually has a solution. Just like some creatures in old field guides turned out to be mythical, some equations are just impossible. For example, take sine of dy over dx equals 2. The sine function, no matter what you put into it, can never be greater than 1. So there's no real-world rate of change that could ever possibly make this equation true.
So, there you have it, your starter field guide to the language of a changing universe. You now have the tools to spot an equation, identify its family, check its vital stats, and know its basic nature. The only question left is, now that you can start to read the language of science, what secrets are you going to try to understand with it?